Hi friends, MoNaCo here. Homework note video 7. We're talking about our first trend in the periodic table. This is the first thing that you're really going to have to, aside from the other things that we've talked about, you're going to have to really memorize and look at this as we go through our notes here. The first trend is atomic radius, and I just want to encourage you to go ahead and do some extra image searches, okay? This is a great little graphic on atomic radius, Google image search. If you look here, simple graphics tell you a great story. The radius increases as you go from the top to the bottom of the periodic table. Kind of makes sense. But what doesn't necessarily make sense is that it decreases as you go from the left to the right. The reason why it decreases as you go from the left to the right is that shielding effect, okay? The nucleus and the valence electrons have more of a pull on each other as you add more protons, so the radius kind of decreases. If that graphic doesn't help you out, maybe something like this does, okay? You can see the elements get bigger as you go down and smaller as you go across, okay? So that's what the main content of this lesson is going to be about. But if we look at the great periodic table, if you do the entire trends, here's why it's periodic. If you graph the radius, it decreases as you go to the next period, as you go across the period, and then you jump to the next period, it jumps back up and then it comes back down. This is a perfect example of a periodic trend. Every time you get to the end of the row in the periodic table, you go to the next one down below. Trend then repeats itself as you go from left to right. So let's get our notes on this material here. Alrighty. Okay. Are all the elements the same size? As you saw in the graphics just a moment ago, no. Because each element is composed of a unique set of subatomic particles, the widths of each element is different. The reasons are different based if we are going across a period or down a group. And the great big answer for why this trend exists is shielding. Okay? So you come to me after you watch this video and say, Mr. MoNaCo, ask me a question about the atomic radius trend. I'm going to ask you, what is the cause for the atomic radius trends that we observe? Your answer should be electron shielding. That's your Easter egg. Okay? So here's a great picture that I kind of just showed you, but this one's in your notes pack. The atomic radius is technically half the distance between neighboring nuclei of a given element. So if you put two potassium atoms together, you measured how big those were across, cut it in half, that's how big one is. Meh. It's kind of like the radius of a circle. In reality, it's how big they are. Moving on. Going down a group, the radius increases. The reason? Orbitals and energy levels increase. As you go down a group, from the top to the bottom, you add more shells of electrons. Logic dictates that there are more shells of electrons, the atom has to be bigger. Okay? Now, as you go across, atomic radius decreases. Oops, sorry. Outside of the atom takes up more space, so I forgot that little note. But as you go across, the radius decreases because of the nuclear charge is increasing, and therefore we have an increase in shielding. Again, I'll draw you a little picture here. All right, so let's imagine we're in period 2, so we only have 2 shells of electrons. But as we go across, we're not adding more shells of electrons. We're just adding more valence electrons to the outside and more protons to the inside. Therefore, the pull that is experienced between the valence shell and the nucleus increases. It's kind of like a pull tug of war. As you add more electrons and protons, they attract to each other because they're oppositely charged, and they cause that atom to actually shrink in size as you go across the table. So while it has the same number of energy levels, they're getting compacted and squeezed in on each other as you go from left to right across the periodic table. We call that the shielding effect. Now, an ionic radius is just like atomic radius, but it's for ions. You just got to memorize something like this. Nonmetals gain electrons, and therefore, if they're gaining electrons, they get bigger. Okay, it's like you add another electron to the outside, it's a bigger atom, or rather, it's a bigger ion. More atoms, more electrons, bigger. The reason, it's got the same nucleus charge, but it's pulling on more electrons. For example, if you do chlorine, if our smartboard would work, if you do chlorine nucleus, it has a plus 17 nuclear charge. It has normally 17 electrons as well. However, if you add an electron to the outside, then it has 18 electrons. Same nuclear charge, pulling on more electrons. So if it would have 18 rings, or 18 electrons on it, 17 versus 18, 18 is going to win. This stuff's going to spread out a little bit, all right? And therefore, you'd add another electron on the outside, and the thing gets even bigger as we go. Now, let's finish that up there. Okay, electrons outnumber the protons. Electrons drift farther away from the nucleus. Metals tend to lose electrons, and the radius decreases. If you lose an electron on the outside ring, whoop, you get smaller. The reason is that you have the same nuclear charge pulling on less electrons. It's like a tug of war. You have the same amount of positive in the middle, less negative on the outside, so they pull at each other a little bit more. It kind of contracts in, pulled close to the nucleus. The isoelectronic series is something new to you. Atoms and ions that have the same number of total electrons. Elements gain or lose electrons in order to attain the electron configuration of the nearest noble gas. We call it the noble gas configuration. All members of an isoelectronic series have the same noble gas configuration. For example, N3 negative, O2 negative, F negative, and Na plus and Mg all have, let me count them up here, nitrogen, 10. They all have 10 electrons. All have the same electron configuration as the noble gas for neon, which is 2-8. Okay? Keep in mind, that's a nitrogen that has gained 3 electrons. Oxygen gained 2 electrons. Fluorine gained 1. Sodium lost 1 electron. And magnesium lost 2 electrons. So by losing or gaining electrons, they all ended up with the same configuration as neon, with a total of 10 electrons in the 2-8 type configuration. That's what it means to be isoelectronic. Things want to be like the noble gases because the noble gases are unreactive and inert. All the elements want to be like them. So they're going to gain or lose electrons, like you see with these ions, in order to get there. Okay, that's the name of the game. Your practice is based upon what we just talked about. Okay, so I want you to make a diligent effort to complete that homework practice. Okay. You might have to watch some of the previous videos, but you should now understand that atomic radius changes as we go down a group and across a period. As you go across a period, it gets smaller. As you go down a group, it gets bigger. You should be able to complete some practice pack pages 15 to 22, 27, and 28. And remember your Easter egg to mention in class. Thanks, everybody. See you later.